Hello again. In the last video, we used the Carnot cycle to derive an equation for efficiency. And the interesting thing about this equation is that the cycle efficiency only depends on the temperature of the hot and the cold reservoirs, and it doesn't depend on other parameters like which volumes we're expanding between. In this video, we're going to show that this same equation can be used to describe the theoretical maximum of any heat engine. The proof of this is conceptual, and so to have the right concept, we should start by mapping our Carnot cycle, our theoretical Carnot cycle, onto the parts of a steam engine that Sadi Carnot was trying to improve when he created his cycle. So in a steam engine, water in a boiler is heated to past its boiling point. Then the water vapor expands, it's heated further and expands, and the expanded gases go into a turbine, and the expanding gases push the turbine blades, and from this we can extract work. The expanded gases then go into a condenser where they're recondensed into liquid water and passed back into the boiler. If instead of a condenser we had a cooler and these were cooled gases, then this turbine would also be compressing the gases into the heater. This whole system is in contact with something we'll call a hot reservoir. So for a steam engine at the time of Carnot, this might have been a wood fire. And the boiler is extracting heat from this hot reservoir, and we often make the assumption that this hot reservoir is so massive or consistent that it remains at a consistent temperature. The condenser is in contact with a cold reservoir. And we make the same assumption that it's thermally infinite and at a consistent cold temperature. The cold reservoir is dissipating heat from the condenser. Instead of using external work to drive this turbine, we could picture that we pick off some of the work from the expanding gas turbine to drive the compressing turbine, in which case we're only getting some net amount of work out. But still, the human is getting work out, so he is happy. John Fenn says that if necessity is the mother of invention, then laziness is his father, and his hypothesis is that laziness drove all of our development of these machines. Okay, so what I'd like you to do now is pause the video and take these structures of a steam engine and map it on to the Carnot cycle. So the Carnot cycle, recall, is two isothermal steps connected by two adiabatic steps. We often start here. This first process here is isothermal compression. This isothermal compression, the internal energy doesn't change for this process. And we're doing compression, so we had to put work in. So before, we concluded that heat was flowing out from this process. Where heat flows out in this system is in the condenser. So our first process here corresponds to what's happening in the condenser. And so on around the cycle. there are a number of ways that this theory may not feel very connected to this engine, but I encourage you to think through why these are matches. Some of the bigger disconnects are, for example, that there's a phase change here, and we modeled the Carnot cycle off of a perfect gas. Another big disconnect that I find people have is that in step 3, which corresponds to the boiler, here the Carnot cycle says that we're extracting work. But in a boiler, there's no device that's converting the expanding gas into work. That doesn't happen until the turbine. So 1, this is a model, and so there are simplifying assumptions. But 2, I encourage you to read in a few places. If this connection isn't comfortable for you, go read about it in a few places to see if you can come to be more comfortable with this mapping. Okay, so next what I would like to do is just have a simpler picture than the steam engine and make it more general. Regardless of what those internal parts are, what I have here is a heat engine, which is a device that pulls heat from a hot reservoir, dissipates it to a cold reservoir, and in the process extracts net work. The efficiency of this process is net work divided by the amount of heat we had to put in. And what drives these two parameters is it's what the human cares about. The human cares about how much work it gets out. And it also cares about how much effort it had to put in to extract this heat. So for example, maybe he's the guy that has to chop wood to keep the fire going for the steam engine. So he cares about this. He doesn't so much care about how much heat is being dissipated on the cold side, because this is probably cooling to atmosphere or something like that. I drew arrows on this engine because we've been going around the Carnot cycle in a clockwise direction. It turns out that if we go backwards around the Carnot cycle, we make another useful device called a heat pump. What a heat pump does is it pulls heat in from the cold reservoir. It uses work, so the human has to put in work. And when the human puts in work, a heat pump will pull heat from a cold reservoir and pump it up to a hot reservoir. It'll pump heat up a thermal gradient. We think differently about the efficiency in this case. We call it coefficient of performance, and its symbol is beta. What the human cares about in this case is how much heat is pulling from a cold reservoir versus how much work he had to put in to do that. And there are two ways we might use a heat pump. One is as a refrigerator. So in a refrigerator, the intention is to make a cold reservoir colder. So we pull heat from a cold reservoir and are thinking about making this side colder. Another reason we might want to make a heat pump or use a heat pump is to make a hot reservoir hotter. So often heat pumps can often be used to heat homes. So we're taking heat and adding it to where it is already hot to make it hotter. And both of those scenarios could make happy humans. So seeing these two things together actually just gave me a brilliant idea. I have a plan. What I'm going to do is I'm going to use a heat engine to drive a heat pump. And when I do that, I'm going to perpetually replenish my hot reservoir, and I will get energy forever without this human having to chop any wood. So let's redraw that scenario. So what I have here is a heat pump that is replenishing a hot reservoir, and it's being driven by some surplus work that's being generated by this engine over here. So this heat pump I'm modeling as a reversible engine, a reversible heat engine run in reverse. So this guy is going counterclockwise. And then over here we're going to invent a really spectacular engine. Our feeling about Carnot is that it was old and surely we can do better than the reversible cycle that he invented so long ago. So we're going to invent something called the Bella Special, named after my dog, who just kind of keeps on going. And this is going to be a spectacular new heat engine that's very efficient. And it's run in the heat engine direction. Boop. So we extract work from the Bella Special, some of which we get to use as the human. and some of which we use to replenish our hot reservoir. So at this point, what I'd like you to do is pause the video and go look up at least 3 definitions or 3 statements of the second law of thermodynamics. Okay. One of the laws that you may have encountered when you just did that exercise is called the Kelvin-Planck statement of the second law of thermodynamics. So the Kelvin-Planck statement says that it's impossible to construct a device that will operate in a cycle and produce no effect other than the raising of a weight in the exchange of heat with a single reservoir. He says raising of a weight, but what he means by raising of a weight is work, because one of the definitions for work used at the time was that work was any type of energy that could be used to raise a weight somewhere. So what he's saying is that it will produce no effect other than work and the exchange of heat with a single reservoir. So let's think about this on our new invention that we're very excited about here because we feel very clever. What I'm going to do is I'm going to redraw the system boundaries here. We are used to thinking of the system boundaries being wrapped right around the heat engine or the heat pump, and instead I'm going to draw a larger system boundary. And when I summarize what's happening around this system boundary, I see that there is a cold reservoir and there's some system that has a net exchange with this cold reservoir and is producing work. But when I draw the system boundaries here, because we're perfectly compensating for the heat we pull out of the hot reservoir with what we put in, there's no net exchange with a hot reservoir. So as I've drawn this system, it's contradicting, or it's conflicting with the Kelvin-Planck statement of the second law. You could also picture that because we're continuously replenishing the hot reservoir, that perhaps this engine would work in perpetuity, and we would call that a perpetual motion machine. This particular perpetual motion machine is called a perpetual motion machine of the second kind, perpetual motion machine of the second kind. If you're curious, you can read about the other two, the first and third kinds. And when you're faced with a conflict like this, you have 3 choices. One, you can conclude by deduction that this heat engine and heat pump combo I've devised is impossible. Your second choice is to choose not to believe the second law of thermodynamics. And after all, none of the laws of physics can be proved. They're just statements that are not disproved over and over again. So one of your options is to choose not to believe the statement of the second law. Your third option is to engage in some creative accounting about where you draw system boundaries and which heat sources that you decide to consider so that you can force this scenario to be in compliance with the second law. Me personally, I'm going to take the first option. I'm going to conclude by deduction that this combination I've devised is in violation of the second law. And that's going to have a consequence for efficiency. So I've redrawn our system here, and because I was able to extract a surplus amount of work from the Bella Special, another way I can think about these engines is that my Carnot reversible heat pump had our usual efficiency, but for this to work, the Bella Special had to have a much greater efficiency. So our initial assumption when we set up our device was that we could make an engine, was that we were clever enough we could make an engine with an efficiency that was greater than the efficiency of a reversible heat engine. That was an initial assumption in this device that we built. We learned that doing this violates the second law. And therefore, we're first to conclude that our initial assumption was incorrect. And from that, we have to conclude that the efficiency of a reversible heat engine is the maximum theoretical efficiency possible for any heat engine. So when we do calculations using this equation, we're basically assuming the best case scenario. We're assuming that the system that we're applying this calculation to is operating with the maximum possible efficiency. So that's the end of this conceptual proof, and there's a lot of things that are nebulous and hard to follow in this proof. I don't think it's possible to learn it just from one run through. I really encourage you to read this proof in your Bergnacki text, in your Akin text. I'm sure it's out there on the internet in a bunch of spots. And if you're still confused, then perhaps you can take comfort in the words of Arnold Sommerfeld, who said that thermodynamics is a funny subject. The first time you go through it, you don't understand it at all. The second time you go through it, you think you understand it, except for just one or two small points. The third time you go through it, you know you don't understand it, but by that time you're so used to it, it doesn't bother you anymore. That definitely feels like my experience of the subject. Okay, thank you. See you next time.